Okay, so one of the most interesting aspects of derivatives is to analyze how a function is behaving close to a point or around a point. Okay, and so they allow us to analyze the local behavior of a function. Okay, in order to do that, we need to first introduce some definitions, and then we'll see some theorems and results that use derivatives to understand the behavior of functions, right? So first of all, we say that a function f has a local maximum at a point a of its domain if there is some interval, okay, and an environment of a minus delta, a plus delta, such that f of x is smaller than f of a for all x in that environment, okay, something like this, right? So that means that point like this, okay, this is f of a, and around this a very short, it doesn't matter if it's short or large, a very an environment of this point a, every point, every f of x is smaller than f of a, right? Smaller or equal. It's the same thing with the local minimum. It's just that instead of being a point around which all of the values f of x are smaller or equal, in this case of the minimum is greater or equal. Okay. We can collectively call local maximum a local minimum, local extrema, because there are extreme points, a point where a function reaches an extreme value, right? And if local extrema remain extrema for all x in the domain of f, they are absolute extreme. Okay, so then we can talk about absolute maximum and absolute minimum. Okay, and obviously there's only one of both, right? Because in order for a function, for a point to be an absolute maximum, it has to be greater than every other value of the function for the whole domain, right? So there's only one of them. That. Okay, and also for the minimum, right? Well, there's an interesting characterization of extrema based on derivatives, right? And it comes from this theorem, right? If f has a local extremum at a point a, right, where it is differentiable, then the derivative at that point is 0. Okay, and that ties in with the geometric interpretation of the derivative that we had talked about. Is that the derivative talks about the increase or decrease of the function at that particular point. Well, if the derivative at that point is 0, that means that the function is neither increasing nor decreasing at the point. So that means that's an extreme. Okay. The proof for this is easy, right? If we have a point a, okay, which is a maximum, well, that means that f of x minus f of a, right? If we come from the left, right, like this, well, f of x minus f of a divided by x minus a, if we are getting close to it from the left, right, it's going to be positive, right? Because the value of f of x is smaller than this, so then the numerator is negative, and then x minus a is also sorry, it's also negative, so this is positive or equal to 0, right? Now if we approach the maximum from the right, this is the limit of this quotient is now the numerator is now negative or equal to 0, and the denominator is positive now. So now this quotient is smaller or equal than 0, right? So, but now the theorem says that at this point a, the function f is differentiable, and because it's differentiable, that means that these two limits must be the same, because the limit when x goes to a of f minus x, fx minus fa divided by x minus a is the derivative, right? So that means that these two limits have to be the same. But because this is greater or equal than 0, and this is smaller or equal than 0, that means that the only possible value for the derivative is to be 0. Okay, these two limits have to be the same and equal to 0. Okay, that's the result. Okay, let's see how do we apply this. Okay, and see some of the limitations of this theorem. Okay, consider this function. The absolute value of x times 1 minus x, which is, in other words, x 1 minus x, whenever this thing is positive. Okay, let me plot this. X times 1 minus x is this parabola, right, which crosses the x-axis at 0 and 1. Okay, this is x times 1 minus x. So it is going to be positive when x is between 0 and 1. Okay, and it's going to be negative, so that we can say this is x times x minus 1 when x is greater than 1 or x is smaller than 0, right? So that means if this is negative, the argument is negative, then the absolute value of that is minus this. Okay, that's what we know about the absolute value. Now, well, if this is the function, let me plot the absolute value of that function. The absolute value will make this be the same, right? And then for the negative part, it would be the same thing but mirrored against the x-axis. Okay, so this is the absolute value of x times 1 minus x. Okay, so let's see what are the extrema of this function. Okay, in order to do that, we compute the derivative of this function. Okay, and so the derivative of this in the in both sides, this is just 1 minus 2x, and this is 2x minus 1. This is valid when x is between 0 and 1, and this is valid when x is greater than 1 or smaller than 0, but we don't know if it's valid in the limit, in the point when these two functions join together. Okay, so we don't know if the function is differentiable at 0 and at 1. Okay, and that's what we're going to see. So the limit when x goes to 0 from the left, okay, of f of x plus f of x minus f of 0 divided by x minus 0, right? From the left, f of x is going to be this. So this is the limit when x goes to 0 on the left of x divided by x minus 1. F at 0 is going to be 0, right? And this is divided by x. So the limit of this is this and this cancel out. This x minus 1, when x goes to 0, this is minus 1. Okay, and you see, right, when you go from the left, this function, the slope of this is negative 1, right? Now, if you compute the limit when you go from to 0 from the right, it's now the limit when you go to 0 from the right of this function, x times 1 minus x, again divided by x. The result is 1, because you see that the slope when you come from the right is positive 1, right? So there's f is not differentiable at x equals 0, and a similar argument will give us the same thing at 1. Okay, so the function is not differentiable at 0 or at 1. Okay, now let's find the points at which the derivative is 0, right? So f prime equals 0 where? So first of all, the first derivative, 1 minus 2x equals 0, this implies that x has to be 1/2. Okay, and at 1/2 we have this point, which is a maximum of the function. Okay, so that corresponds to what we expect from the theorem, right? The function has a maximum at 1/2, right? We can see it here, and because the function is differentiable in this point, then this derivative is 0, right? If we try to find the 0 of this, we get the same thing, but in this case it doesn't work because x, so there's no value that makes the derivative 0. Sorry, this is wrong. It's not f prime material, it's f prime equals 0. Right, sorry. So what I was saying is that there is no value 2x minus that makes this derivative equal to 0 in this interval. Okay, so in the interval that x greater than 1 or x smaller than 1, the function, the derivative is never 0. Okay, so does that mean that this is the only extrema of the function? Well, no, it's not. Okay, as you can see, the value of the function at 0 and 1, which is 0, right? The f at 0 is equal to f at 1, which is 0, are absolute minima, right? Because these 2 points, well, they're local, but both of them are absolute minimum. Every other value of this function is positive, right? If they're not 0, these are the only 2 zeros of the function. Every other point in the domain will give you a positive value. So these 2 are minimum of the function, but we didn't find that the derivative at these points was 0 because the derivative at 0 and 1 doesn't exist, okay, as we have seen before. Okay, so that means that we have to be very careful when applying this theorem to find extrema, because sometimes we need to check also the points where the function is not differentiable. Okay, and so yeah, in order to find the extrema of a function, we need to check the values that make the derivative be 0, but also the points where the derivative doesn't exist. Okay, and also another caveat from this is that if the derivative is 0, okay, it doesn't mean that there is an extrema at that point. Okay, let me write it down. So if f prime at c equals 0, it doesn't mean that that c is an extrema. Okay, remember that what this theorem says is that if there is an extremum at c and f is differentiable at c, then f prime is going to be 0. But the other way around doesn't work, right? If the derivative is 0, it doesn't always mean that this is an extremum. And the classical example is x cubed, right? X cubed works like this, more or less, right? The derivative of x cubed is 3x squared, and the derivative at 0 is 0. So it's clear if I didn't paint it correctly, right? Because if the derivative at 0 is 0, it means that it's flat at here, right? So it's something like this. Okay, at this point this is 0, but this is not an extremum, obviously, because it's not either a local minimum or a maximum. It's a point in which it is that the curvature of the function is 0. Sorry, it changes, but it's not an extremum of the function. Okay, so remember that. If there's an extrema at some point where f is differentiable, then the derivative is 0, but we also need to check where the function is not differentiable, and we also need to check that whenever we find a value of the derivative that's 0, then make it 0, check that it is an extrema, because it can be the case that it's not. Okay. Well, the next important theorem related to derivatives and local behavior is Rolle's theorem. Okay, and it says, suppose f is continuous in this closed interval AB and differentiable in the open interval AB, such that f at A and f at B are the same. Okay, so it's a function that makes something like this, but the value at A and the value at B are the same. Well, the theorem says then exists a C in this interval where the derivative at f is 0. Okay, so for instance, this point here, or this point here, or this point here. Okay, what it says is at least one of them. Okay, let's see. How can we prove this? Well, what we need is to use the intermediate values theorem that we saw in last unit for continuous functions in a closed interval. We know that in AB, right, the function will reach a maximum. Okay, let's see. Let's call x m and x capital M, a minimum and a maximum. Okay, that will belong to this interval, right? Okay, so let's see. Suppose there are some cases, right? That the first case is that both the minimum and the maximum are in this open interval, right? Well, if they are in this open interval, that means that they're extrema in an interval in which f is differentiable. So applying the previous theorem that we have just seen, then the derivative of x at xm and the derivative of x at x capital M is going to be 0, right? Applying the previous derivative. So we're done, right? Well, it could be the case that either xm as xm is a, or x capital M is a, and the other one is at some point c in the wait a minute, in the open interval, right? Okay, so it's either it's A or B. Okay, so one of them, either the minimum is at one of the extremum of the interval, of the ends of the interval, and the maximum is at the middle, and the other way around, right? So we can have two possibilities here, right? Well, if that's the case, then the value of the derivative here is going to be 0, and the value of the derivative here is going to be 0, right? Because applying the same theorem, right? The function is differentiable in this open interval, and it's reached an extrema here, right? So that's the second possibility, right? The third possibility is that the maximum is at B, for instance, and the minimum is at A, or the other way around. The minimum is at B, and the maximum is at A. But now the thing is that we know that the function has the same values at fa and at fb, right? And so that means that the minimum and the maximum are the same, right? F at xm is equal to f at xm. But we know that this is the smallest value that it has, and this is the greatest value that it has. So that means that f is constant in this interval. Okay? And so that means that if a function is constant, we know that the derivative f prime will be 0 for all c in this open interval. Okay? That's just the three possibilities that result in us having a point c where the derivative is 0. Okay? Now, from Rolle's theorem, we can get another one of the most important results in differential calculus, which is the mean value theorem. It says, suppose f is a continuous function in closed AB and differentiable in open AB. Then there is a c, okay, in that open interval, such that this thing is true. F at b minus f at a is equal to the derivative at a c divided by b minus a. Okay, the graphical interpretation of this is that suppose we have this right function f, right, at a and at c and at b. Well, if we compute the difference between fb minus fa divided by b minus a, as we talked about in the first video in this unit, this is just this difference, right? This slope. Okay. Well, what this is saying, so this is the slope of this line, right? What this is saying is that there's a point C in which the derivative at this point is the same as this line, right? So, for instance, this point here. Okay. And this is true as long as these hypotheses are met. Okay, the proof of this uses Rolle's theorem, applying this to this function. Okay, and then if you check that, you will see that g at a it will be the same as g at b, right? And then you can check that this function is continuous. It's also differentiable in the interval, and then you need to check that the fact that there's a g a value g such that g prime at c is 0 implies this result. Okay, so I'll leave you to do it on your own. Okay, practical consequences of Rolle's theorem, okay, is that we can characterize the behavior of a function in an interval depending on the value of its derivative. Okay, so supposing that the function is continuous in closed AB and differentiable in AB, we can say these things. If the derivative of x is 0 for all the values in the interval, then f is constant. Okay, not only the other way around, right? If f is constant, we know that f prime is 0. Well, the other way around works well, right? If a derivative is 0 for all the values in the interval, then the function is constant in that interval. And the proof for this is easy, right? If we write fy minus fx, where x is smaller than y, and these two guys are between a and b, right? Then we write using the formula from the mean values theorem, right? Now, if f prime is 0, that means that f prime is 0 for all c in the interval. That means that f at y equals f at x for all x and y in this interval. So that means that f is constant. Okay. Now, the second application is that if the derivative of f x and the derivative of g are the same in a whole interval, then these functions will be the same but separated by a constant in the interval. Okay, and you just need to apply this first part to a function. Let's call it h. It's f minus g, right? Well, if we call this is part 2. At h prime, right, will be f prime minus g prime, right? Well, if h prime is 0 for all x in the interval, right, then that means that h is a constant k. So that means that f is g plus a constant. Okay. And if the derivative here is 0, that means that these two derivatives are the same, which is what this is saying, right? Now, for the third part, if the derivative is positive in all the interval, then f is strictly increasing, right? Again, applying this, f y minus fx equals f prime times y minus x. If f is positive, this is positive, so this is greater than 0, so that means that f at y is greater than f at x, so that means that this is strictly increasing. And the same applies for the negative derivative. Okay, so if the function has a negative derivative in an interval, it is strictly decreasing. Okay. Okay, so let's see if we can apply all of this to an exam. We're going to get the function fx 2x to the 5/3 plus 5x to the 2/3, and we want to see or to find the extrema in this interval, minus 8, 1. Okay, so first of all we have to find f prime, okay, and see where it is valid. Okay, so this is 10/3 x, and then this is minus 1, so this is x to the 2/3, and then we have plus 2/3 x to the minus 1/3, right? And now well, this is okay, this is going to be continuous in the whole interval, but this is not going to be continuous at 0, right? At 0 this is not defined. Okay, so we can, this is valid for x different than 0. Okay, and then we have to, so the first step is to find the values that makes the derivative 0, and then check if they're local extrema, then find the values where the derivative doesn't exist, so that's at 0, and then we need, in order to check if they're extrema, we need to compute the sign of the derivative on the left and on the right. Okay, so for instance, for a maximum, you will have that the derivative on the left is positive and the derivative on the right is negative. Okay, so you need this, and for a minimum, you need the other way around. You need negative on the left and positive on the right. Okay, and then we have all the local extrema, and from that we can get the absolute extrema by comparing, right? Okay, so let's first compute the values that make this derivative 0. Well, we have said this is not valid at 0. Let's see what's the derivative at 0. We have the limit when x goes to 0 of this, right? F at x minus f at 0, which is 0 divided by x, and so this is the same as the limit when x goes to 0 of 2 to the x 2/3 plus 5 to the x of minus 1/3, and the problem is that this limit doesn't exist because the two how to say this, that this is divergent. Okay, so it doesn't exist, so the function is not differentiable at 0. Okay, so first let's see what are those that make the derivative equal to 0, right? So let's see, we can rewrite the derivative as 10/3 times x plus 1 times x to the minus 1/3, right? So there's only one value of x that makes this equal to 0, which is f prime at minus 1, which is 0. Okay, now if x, we want to check if this is a maximum or a minimum, right? So if x is smaller than minus 1, right, then we have that this is going to be negative, and this is also going to be negative, right? So the derivative is going to be positive. And then if x is smaller than minus 1, then this is negative again, close to it, right? This is negative, this is negative, and then this is going to be positive. So we have that f is going to be negative. Okay, so we have positive on the left and negative on the right. Minus 1 is a maximum, okay, a local maximum. And then we have, so that's for the values that make the derivative 0, right? Now we want to see what happens at 0, right? So f at 0 is, well, let's see, f at minus 1 is 3. Okay, you can compute it, because this is minus 1 to the 5/3 is minus 1. So 2 times minus 1 minus 2 plus 5 is 3, right? F at 0 is 0 again, but what happens with f of x when x is smaller than 0? Sorry, the derivative on the left of the of this point x equals 0, then this is going to be positive, and then this is going to be negative, so this is negative. And the derivative when x is greater than 0 is going to be positive, because this and this are positive values. Okay, so we have negative, positive, and we know that there's a cusp here because 0 is not differentiable, so this is a minimum. Okay, so we have a minimum at 0, a maximum at minus 1. Okay, and now, because we're checking the values, the extrema of the function at minus 8 sorry, and this at this closed interval, we need also to check the value of the function at -8. If you compute this, this is -44, and the value at 1 is 7, and we want to check the derivative at x, when x is greater than -8, well, around -8, right? It's going to be positive, okay, because again, this is negative and this is negative, and the derivative when x is smaller than 1 is going to be positive again, right? So we have that this thing is in the left extremum of the interval, right? And then we have this point -44, and the derivative is positive here, right? At this point, and this here on the so this is going to be a minimum, right? And for f at 1, it's going to be this value 7, and again the derivative is positive on the left, so that means that this is going to be a maximum, okay? And so let me see. So taking this all together, we have that f at -8 is -44, and we know it's a minimum. Okay, so we also need to check the values of the function at the string. F at -1 is 3, and we know it's a maximum. F at 0 is 0, and we know it's a minimum. And f at 1 is 7, and we know it's a maximum. Okay, if you take all of this information and plot this function, okay, this is -8, this is 1. Well, this is coming from negative here, and then there's a maximum here at 3, right? This is -1, this is 3, there's a 0 here, and there's a 7 here, something like that, okay, and something very small here. So what this is doing is the derivative is positive up until here, right? So the function is increasing, it gets to this maximum, and then the derivative is negative up until it reaches to 0. Now here it's not differentiable, so now after which the derivative is positive, so you have this, okay? So with this information, this characterization of the function with the derivatives, we can get an idea of how the function behaves, right? And we can get this kind of not very precise drawing of the function, but a very qualitative behavior of the function, right? Which is important. Okay, well, we have another theorem, which is Kushi's mean value theorem, which is similar to the mean value but applied to different function. So suppose f and g are continuous in the closed interval ab and differentiable in open ab. Then we have a c in this open interval such that f at b minus f at a times the derivative of g at c is equal to g at b minus g at a times the derivative of f at c. Okay, so it's kind of an extension of the mean value theorem. The mean value theorem is actually a particular example of this more general theorem. Okay, and you can prove it using Rolle's theorem, applying Rolle's theorem to this function. Okay, and again you have to check that h at a is equal to h at b, and that is differentiable in the interval, continuous, and so on and so forth, and then you will get to this formula. Okay, but we mentioned Kushi's mean value theorem because it is an important element in the proof of this rule that all of you know, which is L'Hopital's rule. Okay, and it is an important tool that we have in order to compute limits using derivatives. Okay, so it says, suppose we have f and g, two functions, such that the limit when x goes to a of the fraction, the quotient between the derivative of the two functions is some value L, right? Well, if the limits of f and g are both 0 or plus or minus infinity at a, then that means that we have an indetermination, right? Because we have the limit when x goes to a of f divided by g is either 0 or 0, or plus infinity, or minus infinity, right? It's one of these possibilities. And this is an indetermination. We don't know how to solve it. Well, L'Hopital's rule says if this is the case, then this limit is the same as the value of the limit we obtain with this, okay? But provided that this limit exists. And this is important because in some cases it will not exist, okay? So let's see some examples of this, okay? For instance, we have the limit when x goes to 0 of the sine of x divided by x. We know that this is going to be 1, but this is just 0 divided by 0, right? So applying L'Hopital's rule means that if we compute this limit, the limit of the derivative, okay, and this exists, and in this case this limit is 1, right? Then this limit is exactly the same as this limit, okay? So it is only because this limit exists. We're going to see later an example in which this doesn't work. Okay. So for instance, compute the limit when x goes to 0, e to the x minus the cosine of x divided by the sine of x squared. Well, again, this is going to 1 minus 0 minus 1, 0, the sine of x squared, 0. Okay. So now we need to compute the derivative of the numerator. So this is e to the x minus 1 plus the sine of x divided by, and then we have 2x. Okay, this is the chain rule. We have to derivative of this times the derivative of the cosine at x squared, right? And now we have, this is 1 minus 1, 0 plus 0 divided by 0, again the derivative, it's 0 divided by 0. Well, we have to compute the derivative again. So this is e to the x plus the cosine of x divided, and now we have 2 times the cosine of x squared. Now we have the product rule, plus, and then 4x squared sine of x squared. Sorry, minus, because the derivative of the cosine is minus. And now we have, this is going to be 2, and then this is going to be 2 minus 0, 2, the limit is 1, okay? So now we can say that this is equal to this. So this is, I'm not doing it very rigorously because we don't know if this is equal to this unless this exists, and we don't know if this is equal to this unless this exists, okay? So if you get to something that doesn't exist, then these equalities would not be the same, okay? So just have that in mind. Okay, so you can use L'Hopital's rule to prove these asymptotic equivalences that we have seen before, right? So 1 minus the cosine of x is asymptotically equivalent to x squared over 2, which means that the limit when x goes to 0 of 1 minus the cosine of x divided by x squared divided by 2 is 1. So we can compute this limit using L'Hopital. The same thing with the tangent in x, e to the x minus 1 and x, the logarithm of 1 plus x and x, and then 1 plus x to the alpha, approximately equivalent to alpha times x. This is new, we haven't seen this before, so it's an important one. You can prove this using L'Hopital's rule, okay? And this is an important remark from the definition of limit that we have seen, right? The limit when x goes to infinity, for instance, of f of x is the same as the limit when n goes to infinity. This is a typo. The limit when n goes to infinity of f at n divided by g at n, right? And so instead of, because you know we have this sequence xn equals n is a particular sequence that goes to infinity, okay? And we know that if this limit exists, that means that all the sequences that go to infinity have this limit, okay? So n is one of those sequences. So that means that we can apply L'Hopital's rule to sequences, to limits of sequences as well. Okay, and in particular, we can use this as a variation instead of Stoll's theorem. Okay. Okay, so now let's see one example in which L'Hopital's rule doesn't work. Okay, so suppose we have this limit. The limit when x goes to 0 of x squared times the sine of 1 over x divided by the sine of x, right? Now we know that the sine of 1 over x when x is very small, sorry, not the sine of 1 over x, the sine of x when x is very small is approximately equal to x. So this is the limit when x goes to 0 of x squared times the sine of 1 over x divided by x. X squared and x cancel out, so then you have the limit when x goes to 0 of x times the sine of 1 over x, which we know is 0 because the sine is bounded and x goes to 0, right? Now we try to compute this using the L'Hopital's rule. Okay. Well, we differentiate the numerator. We have 2x, the sine of 1 over x, and then we have minus 1 over x squared times x squared gets 1, and so you have the cosine of 1 over x divided by the cosine of x, right? But now this denominator is going to be 1, right? This is going to be 0, so you have the limit when x goes to 0 of the cosine of 1 over x. This limit doesn't exist. Okay, so we can't say that this is equal to this. Okay, and so that's a very important caveat when using L'Hopital's rule, and a very important limitation of it as a technique. And how to say this, that this is not an infallible technique in order to compute limits. Whenever you do this and then find that the limit doesn't exist, then you can't deduce from it that the original limit doesn't exist, because it does, as we have seen here. Okay, and so as we will see in the next unit about Taylor expansions, I think it's a much more sensible approach to computing limits to use Taylor expansions, which is an extension of these asymptotic equalities, but in a much more organic way, and it's a more general technique than L'Hopital's rule. It always works, it never fails, and it's not. I feel it's much more interesting, but we will go into that in the next lecture.